Sticking with our implicit differentiation, we're going to extend it a little bit and we're going to find higher order derivatives. I still could find the acceleration of a function that is dependent on x and y. So we've got to see what happens there. So the first thing I need to do is take the first derivative. So my first derivative here, I'm going to have 2y dy dx minus 2x equals 0. So to isolate my dy dx, I'm going to add 2x to both sides, which gives me 2y dy dx equals 2x, and then I'm going to divide by 2y. So my derivative of y with respect to x is x over y. So there's my first derivative. So now if I want to know the second derivative, I have to take the derivative of this guy. So that's going to involve quotient rule. And when I write the second derivative, it looks like this, okay, because it's the second derivative with respect to x twice. So we get this notation here. So I'm going to have low d high minus high d low all over low squared. All right, so this is where higher orders with implicit gets a little bit interesting. I have a dy dx. For this derivative, we had a dy dx and we isolated the dy dx. That's the whole point of finding that derivative. But here, I'm looking for the second derivative and I already have that isolated. So what do I do with my dy dx? This is kind of cool because we already know what dy dx equals. So we can go ahead and take this and substitute it in. I'm going to erase that line now. But we get that idea, right? I'm going to plug it in. So this is going to give me y minus x times x over y squared. Okay. Now that I've made that substitution, I'm just looking at some algebra to simplify this. I have fractions in the numerator, so I'm going to get a common denominator by multiplying by my first y by y over y. So that's going to give me y squared minus x squared, x times x, over y, all over y squared. So I have a fraction inside of a fraction, so what I'm going to do is I'm going to do my copy dot flop. And I'm now looking at y squared minus x squared over y cubed. So there's my second derivative. Okay, the only twist here is we had to make that substitution for our dy dx. But we've got a little treat here. Here I have y squared minus x squared. Does that feel familiar? Well, y squared minus x squared equals 5. That's from my original function. So I can come in, I can make that substitution. So my second derivative is 5 over y cubed. Okay? That's not going to happen every time, but it sure is cool when it does. Okay? See what you can do.